This comes out of section 5.3, concavity and points of inflection. As we kind of continue to fill in the picture about how to draw a curve sketching chapter, so far we've kind of talked about, we always knew how to find points, so we might have a point A and a point B on a graph, and maybe I'll have a similar situation over here, point A and point B, and we might even know that this graph increases on that interval from A to B, which makes sense given where they are, but the picture still doesn't necessarily come straight from that, because you might have a picture that curves upward in this way, or a picture that curves down in that way, or even a picture that it has a straight line connecting those two dots. And so what we get into is something called concavity. This first picture I've sketched here is called concave up, and the second one is labeled as concave down. And what you'll see if you look at even tangent lines on this curve, if I look at just to the right of point A, I have a positive but not very large slope of the tangent line, and it gets bigger and bigger and bigger. So you could say that the first derivative is increasing. It's kind of a weird thing to say, but what that basically means is that the second derivative needs to be positive. So what we find is when something is concave up, its second derivative is actually positive. And the opposite being true, if you take a look at the slope of a tangent line close to A, it's relatively steep and gets less so as you get closer and closer to B. And so what you have are the first derivative is decreasing, meaning that the derivative of that, the second derivative, must be negative. And so we have actually a fairly straightforward test for finding whether something is concave up or concave down. Now, if I draw kind of a generalized, strange-looking function here, where it's got some curve to it, has a strange little cusp on it here, and I label some points. I've got point R, point S. I'll call this one point T, and over here point U. So R, S, T, and U. We have points that are neither concave up nor concave down in this scenario. If I don't have the function here written out, but if I just call this f of x, the second derivative of this function is 0 at these points. These points are changes of concavity, R, S, and U, that is. R, S, and U are what we call points of inflection. A point of inflection is just a place where the concavity changes. So at point R, you're going from concave up to concave down. At point S, you're going from concave down to concave up. Point T isn't a point of inflection because we're concave up, and then to the right of it, we're concave up again. So there's not a point of inflection there. And point U is going from concave up to concave down. So our points of inflection is a similar kind of a test or analysis that we did with the first derivative when we were looking for something, whether it was a max or a min. We basically, if something was going to be a max, the graph had to increase and then decrease. If it was going to be a min, the graph had to decrease and then increase. While if something's going to be a point of inflection, it has to go from concave up to down, or from down to up. And so if you have a change in sign of the second derivative, you have a point of inflection. So what we do basically is find anywhere where the second derivative is 0. If you find the second derivative 0, you might have a point of inflection. And we test to the left, to the right, to see if it changes concavity or not, because there are these unusual places where the second derivative might be 0 or even undefined, and you don't have a point of inflection at all.